Let's start by looking at how neural networks are used inside reinforcement learning. In modern reinforcement learning setups, these networks basically take the place of lookup tables. Instead of storing values in a table for each state or action, the network tries to approximate them, usually value estimates or action probabilities, especially when the number of states is large or continuous. And the main idea here is that we are using a neural network to approximate some function that would be impossible to store or write out directly. And that's why methods like Q-learning, when paired with a deep network, are able to handle complex environments like video games or robotic movement without falling apart. And let's move to how this is structured. We are looking at a simple architecture used in deep Q networks, or DQN for short. This kind of model takes in the state. For example, the pixels of a frame or the current sensor readings, and pushes that through a series of fully connected layers. The output gives us Q values for each possible action. And in this visualization, you can see the network layout. On the left is the input layer. That would be your state representation, maybe your values if you are in a simple environment. Then we pass that through two hidden layers. These are just fully connected layers with some non-linearities in between. And finally, on the right, we get two outputs. Here, two dots. And those would be the Q values for the two possible actions in this case. Say move left or right. So what we are doing here is learning a mapping from states to Q values. During training, the network updates its parameters so that it gets better at predicting the expected return of each action. And let's go over the second structure, which is the actor critic method. And what is that? This one works a little differently. Instead of using a single network to estimate values, it splits the job into two. One network, I mean the actor, decides which action to take. The other one, the critic, evaluates how good that action was. And you can think of it like this: the actor is proposing something and the critic is giving feedback. That way, learning becomes more stable because the policy is not trying to directly guess the best action from scratch. It's guided by the critic. Usually it looks similar. We still have input, two hidden layers and outputs, but behind the scenes, these may be two separate networks or a shared backbone with two different heads, one for policy and one for value. And during the forward pass, both the actor and critic networks process the state to compute their outputs. And moving on, here is proximal policy optimization, or PPO. This is another policy gradient method, but it has some improvements for stability. One issue in standard policy gradient methods is that if you take too big of a step during learning, performance can get worse instead of better. PPO tries to prevent that by using a clipped objective function, which basically just means it doesn't let the policy update too far in one go. It keeps things from changing too aggressively. And architecturally, it can look similar to Actor Critic, and it often is built on top of the same idea. Again, we have got state inputs, hidden layers, and output units representing either action probabilities or direct action outputs depending on the settings. And as you can see here, observe state phase. This is where the agent collects data from the environment before doing any updates. And each phase in this process, observe, act, learn, feeds into the next. And the network keeps adjusting itself based on feedback from the environment. That's done. Now, let's talk a bit about the main functions that neural networks handle inside reinforcement learning. The first one is value function approximation. That just means we are using the network to estimate how good it is to take a particular action in a given state. These are the Q values. The agent uses them to choose actions that are expected to give higher rewards over time. And if you look at the DQN example, it is straightforward. You fit in the state and the network spits out Q values for all possible actions. For something like an Atari game, this could mean using convolutional layers to process images and then fully connected layers to calculate the final values. Alright, now on to policy representation. Instead of learning how good an action is, the network directly learns what action to take. So we are mapping states to actions or to action probabilities. This is useful especially when you are working with continuous actions or when you want to avoid estimating values altogether. Actor-critic models handle this by splitting things up. One part of the network suggests an action, that's the actor, and the other part scores it, that's the critic. Sometimes they share layers, sometimes they are built completely separately. And let's move on to quick comparison across three popular algorithms. Starting with DQN, this uses a value-based approach. The action space is discrete, and some of the standard features include things like experience replay, where past transitions are reused during training, and target networks, which are slow moving copies of the main network used for stability. And let's look. There's also epsilon greedy exploration, which means the agent still chooses random actions some of the time just to keep learning. Then we have got actor critic. This combines value and policy learning. It can handle both discrete and continuous actions, and the benefit here is reduced variance in learning. Basically, it makes training smoother compared to just using policy gratings alone. And finally, PPO, proximal policy optimization. This one is similar to actor critic in terms of network structure and action types, but it adds a clipping mechanism to the update step that helps prevent the policy from changing too much at once. It also allows multiple passes over the same batch of data, which makes it a bit more efficient. And tuning PPO is usually easier, and that's part of the reason why it is so popular. Okay, now let's look at some real world use cases. First, robotics. Neural networks allow robots to learn how to move, grasp, and interact with their surroundings. Whether it's a robotic arm learning to pick things up or a bipedal robot trying to walk, these systems rely on sensory input processed by a network. And next, autonomous vehicles. Here, reinforcement learning helps with decision making in complex driving situations. The vehicle needs to plan its path, avoid obstacles, and respond to changing environments, all based on continuous input data. Neural networks make that possible. And here's resource management. This includes things like optimizing how much power to allocate across servers in a data center or controlling cooling systems to save energy. The system learns which actions reduce costs or improve efficiency over time. And thank you for listening. That's all for this lesson.